Bismillah ar-Rahman ar-Rahim. Today we will talk about chapter 24, lecture 2, capacitance and dielectric. In this lecture, we will discuss the energy storage in the capacitors and the electric field energy, and then we will finish this lecture by the discussion of the capacitors with the dielectrics. At first, let me introduce the expression of the energy stored in the capacitors. Suppose that at some instant during the charging process, the charge is Q and the potential difference is delta V. The work necessary to transfer an additional charge dQ to the capacitor will be dW, of course, because we are talking about dQ. So, and dW here, it's going to be delta V, the potential difference multiplied by the amount of charge dQ. However, we know that delta V is equal to Q over C, of course, because in the first lecture, we said that C equal Q over delta V with the absolute value. Okay, so then the total work required to change the capacitors from 0 to the charge Q is W, the integral of dW. And don't forget to substitute this dV by the delta V by Q over C. So we're going to get the integral from 0 to Q of Q over C. This is what we call delta V, Q over C multiplied by dQ. And here our variable is the charge Q. So we're going to get 1 over C as its constant, Q dQ from 0 to Q. So we're going to get W, the work required to transfer the additional charge dQ is equal Q squared over 2C. Okay? Since the work done in charging the capacitor can be considered as potential energy U stored in the capacitor, as there is no loss of energy, so we can write that the potential energy is half of Q squared over C. Don't forget that we can substitute Q by C delta V, and we can get these two equations. So let's try to do it with the first equation. So as you know here, the potential energy is equal to half 1 over 2 C multiplied by Q squared, and Q squared is C squared delta V squared. So here we can simplify by C, and we're going to get half of C delta V squared. And we can do the same thing to get the other expression, okay? So what is the potential energy stored in the capacitor? It can be expressed in terms of Q and C, can be expressed in terms of Q and delta V, and then can be expressed in terms of C and delta V. So it's going to be half of Q squared over C, which is equal half of Q delta V, which is equal of half of C delta V squared. So the question here, which equation that we're going to use? So based on the given of the question, we can decide which equation that we are using. The total energy, the energy stored in the capacitor can be considered as being stored in the electric field created between the two parallel plates of the capacitor, of the charged capacitor. Let's talk about this a little bit. If we consider a parallel plate capacitor, as you know in chapter 24, lecture 1, the capacitance is equal epsilon naught multiplied by A over D. A is the area of these parallel plates, and D is the distance between the two parallel plates. Don't forget that we have that delta V is equal the electric field multiplied by the distance between these two parallel plates. Recall that the potential energy is equal half of C delta V squared. If we substitute this C by the expression epsilon naught A over D, and if we substitute the potential difference by ED, we're going to get half of epsilon naught A over D, which is the capacitance, multiplied by ED squared, which is the potential difference squared. So here we can simplify by D, and we're going to get the half of epsilon naught E squared multiplied by the area of the capacitors and of the plate of the capacitor and the distance between the two parallel plates. Area multiplied by a distance gives a volume. Okay, so it's the volume between these two parallel plates. So where AD is the volume occupied by the insulator between the two plates. We call this quantity half of epsilon naught E squared, the energy per unit volume, or we can say the energy density in the electric field. So you can see here that the energy density depends on the square root of the electric field. So we can say that the electric potential energy of the capacitor is stored in the electric field. So the energy density is proportional to the square of the electric field in the unit volume. It's okay. So خلاص, we are done. This is our equations. The first equations are for the potential energy. The second equation is for the energy per unit volume or the energy density in an electric field. Let's take some examples. In this example, we have a capacitor C1 equal 8 microfarad. This is C1. 8 microfarad is charged by connecting it to a source of potential difference V0. The switch S is initially open, so there is no capacitor here. It's open. Once C1 is charged, the source of the potential difference is disconnected. At first, question A, what is the charge Q0 on C1 when the switch S is left open? Let's try to do it step by step. Okay, so the question said, what is the charge Q0 on C1? Q0, as you know, it's C1 multiplied by V0. Yes or no? Yes. We know that C1 is 8 microfarad, so it's equal 8 microfarad. Well, that means we can write times 10 power negative 6 multiplied by C1, which is 120 volt. So the result will be how much? It's going to be 960 microcoulomb. So that means times 10 power minus 6. Or we can say 960 times 10 power minus 6, and the unit is coulomb. So this is the initial charge of the capacitor after has been charged. Okay, let's move to the question B. And the question B, what is the energy stored in C1 when the switch is still open? Question B. As you know, I will write all the formulas here. The energy stored in the capacitor is half of C delta V squared. Let's say this is C1, and let's say this is V0 squared, according to this question, which is equal half of Q0 V0, which is equal half of Q0 squared divided by C1. Okay, so which equation that we're going to use? From my side, I prefer to use the equation in terms of C and C1 and V0. Why? Because these are the given of the question. Sometimes the students make like mistakes in the calculation of Q0, and then they will use Q0 in the determination of the energy. So they can make another mistake. So based on that, I prefer to use the first expression of the energy stored in the capacitor. So we can say that the energy stored in the capacitor C1 equal half of C1. C1, we said it's 8 times 10 power minus 6 multiplied by 120 volt squared. So the result will be 0.058 joule. And we are done with the second part, with the second question. Let's move to the third question. Now, C2, which is equal 4 microfarad, is initially uncharged. After the switch, what happened to the switch? Now the switch is closed. What is the potential difference across and the charge on the capacitor, on each capacitor? So this question is composed of two questions. It's asking about the potential difference after removing the battery and connecting the two capacitors in parallel. And he's asking also about the charge on each capacitor. So let's try to do it. Question C, part 1. He's asking about the potential difference. As you know, this is the capacitance C1, and this is the capacitor C2. Okay. Before, the potential difference of the battery was 120 volt. Now, what happened to this potential difference? We will see. So this is delta V. So let's say this is V2 or V. What he said here? Nothing. So let's say this is V. Okay. This capacitance is equal 8 microfarad, and this capacitance, he said, it's 4 microfarad. Okay. Now these two capacitors are connected in parallel. The two sides of the capacitors are connected to each other. So we can say that, what we can say, delta V or V equal Q total divided by C equivalent. Since they are connected in series, so C equivalent will be in parallel, so C equivalent will be their sum. So we can write C1 plus C2. And what happened to this charge? They are connected parallel. So we can say that the charge Q naught is the sum of the charge Q1 plus the charge Q2. So it's the sum of the charge on the first capacitor plus the charge of the charge on the second capacitor. So we can write here, it's going to be Q naught. Okay. And the charge, or the initial charge of the capacitor, will be divided between these two capacitors. Why? Because they are connected in parallel. Okay. So we can say that it's equal Q naught, how much? We said it's 960 microcoulomb divided by C1 plus C2. So we can write 8 plus 4 times 10 power minus 6, because it's in microfarad. So we can cancel this 10 power minus 6, and we're going to get 960 divided by 12. So the result, V equal how much? It's 80 watt. That sounds good. Okay, so we are done. This is the first part of the question. What is the potential difference? The potential difference is the same. Why? Because they are connected parallel. Okay, because they are connected in parallel, and it's equal to the total charge divided by the total capacitance. Let's continue. He's asking about the charge on each capacitor. Part 2. For the capacitor C1, what is the charge Q1? We said it's C delta V. C1, V1. So it's going to be C1, we said it's 8 times 10 power minus 6 times 80 watt. Now, the first battery has been removed and the two capacitors are connected in parallel. So we're going to get 60. How much? It's going to be 64. Where is it? $40 microcoulomb. What about the second capacitor for C2? What we're going to get? Q2 equal C2 multiplied by V1. Let's say this is V1. Let's say this is V1. Okay, so it's going to be C2 how much? We said it's 4 times 10 power minus 6, because it's microfarad, multiplied by 80. So it's going to be 320 microcoulomb. And we are done. This is the question C. What is the total energy of the system when the switch S is closed? For the total energy of the system, U total, it's going to be the energy stored in the first capacitor plus the energy stored in the second capacitor. Okay? We can write it's equal half of Q delta V squared of C or C delta Q squared or C delta V squared of Q delta V or Q squared over C, so whatever. So here we can use C delta V squared, for example, C1 V1 squared plus the half of C2 V2 V1 squared. Both of them, they have the same potential difference because they are parallel. So we can write it's equal the half of C1 plus C2 multiplied by V1 squared. So the result will be U total equal half. C1, how much? We said it's 8 plus 4, both of them microfarad, multiplied by 80 squared. So the result will be 0.03938 joule, 0.038 joule, and we are done. You see that the question is very simple, very easy, and we can do it in a couple of minutes. Okay, now we will take another question. Suppose you want to store 1 joule of electric potential energy in a volume of 1 meter cube in vacuum. The question is, what is the magnitude required of this electric field? That's very good. So what we're gonna do, as usual, we want to solve step by step. In this question, he said, what is the magnitude of the required electric field? As you know, the energy for the two parallel plate capacitors is equal what? The half as a function of the electric field here. Epsilon naught E squared. This is the electric potential energy, the density of the energy multiplied by the volume. Okay. So that means our electric field E will be 2 multiplied by the energy divided by epsilon naught multiplied by the volume, and don't forget that it's under the square root. So we're gonna get 2 times the energy. Our energy is 1 joule divided by epsilon naught 8.85 times 10 power minus 12 multiplied by our volume, which is 1 meter cube, under the square root. So what will be the result? E equal how much? It's going to be 4.75 times 10 power 5. 4.75 times 10 power 5 volt per meter. Or we can say Newton per coulomb. Okay, so this is the first question. Let's move to the second question. And the second question, if the field magnitude is 10 times larger, how much energy is stored per meter cube? So as you know, from the previous question, shows that the energy density is proportional to E squared. Now, if E is multiplied by 10, so that means 10 E naught squared. So it's going to be 100 E naught squared. So it's going to be multiplied by 10. It's okay. So if E increases by a factor of 10, the density increases by a factor of 10 power 2. That means 100. So the energy density becomes 100 joule per meter cube. Okay. Let's move to the second part of this lecture. Now, in the previous parts, we said that the capacitor, the parallel plate capacitor, is separated by a vacuum. There is nothing between the two parallel plates of the capacitor. Now, we will try to insert the dielectric, and we will see what happened to the charge, to the capacitance, and to the energy after inserting the dielectric between the parallel plates of the capacitor. At first, let's define what means a dielectric. As you know, a dielectric is non-conducting material, so it's an insulator. Most capacitors have dielectric between their plates. For example, here in our case, it's plastic sheet. The dielectric between the two conductors is a plastic sheet. The dielectric constant of the material is always greater than 1. Kappa is always greater than 1. The dielectric increases the capacitance by a factor of kappa. So that means the capacitance after the dielectric is going to be kappa multiplied by C naught, and which is greater than C naught, because kappa is, is greater than 1, so the capacitance will increase. The figure, the lower right, the figure shows how the dielectric affects the electric field between the plates. So initially, we have two parallel plates. The first is charged positively with the charge density sigma. The second one is charged negatively with the charge density minus sigma. The two densities are equal in magnitude or in absolute value. So there is an electric field that will be built up between these two parallel plates from the positive to the negative always. And we will call this electric field E naught before the dielectric. Now, if the dielectric is inserted between the two parallel plates to fill up the space between the plates, so what we're going to get? There is a polarization. And there is induced charge on the left side, and this induced charge are negative because the plate is positive, so they will be attracted. And there is induced charge, positive induced charge on the right side of the dielectric, attracted by the negative charge of the plate. And here there is the appearance of another electric field, and this electric field is induced and has a low magnitude. For a given charge density sigma, the induced charge on the dielectric surface reduces the electric field between the plates. And the resulting electric field after the dielectric will be less than the electric field before the dielectric. Okay, because there is an induced electric field. Here, some values of the dielectric constant are 20 degrees. For the vacuum, as you know, is 1. For the air is 1.00059, and so on. Now, let's come back to our characteristics, the characteristics of the capacitors. When a dielectric material is inserted between the plates of the capacitor, the capacitance, as we said, it's increasing, and C equal kappa multiplied by C naught, and it's increasing. What's happened to the potential difference? The potential difference decreases by a factor of kappa. So the potential difference will be delta V naught over kappa. And since kappa is greater than 1, so this will be decreasing. Okay. What happened to the energy? Energy also is decreasing. When a dielectric material fills the space between the plates of the capacitor, its capacitance increases by a factor of kappa, call it the dielectric constant. So for the two parallel plate capacitor, this is the capacitance C naught, as you know, epsilon naught A over D. It's going to be multiplied by kappa after the dielectric and gives the capacitance of the dielectric, of the capacitor after the dielectric, which is increasing comparing to C naught. The figure below shows the polarization of the electric field and how induced charge reduces the magnitude of the resultant electric field. As we discussed right now, we have two parallel plates. The first plate is charged positively on the left. The second one is charged negatively on the right. There is an electric field pointing from the right, from the positive to the negative, so it's pointing to the right. After the dielectric, just the dielectric is inserted. So there is nothing, just a few seconds in the order of microseconds or nanoseconds, a small amount of time, there is a new electric field due to the polarization. What means polarization? There is induced electric charge, negative, on the left side attracted by the positive charge of the plate, and there is a positive charge attracted by the negative charge of the plate. And here we have a new distribution of charge inside this dielectric, negative and positive. And the electric field inside the dielectric, and in addition to the initial electric field, it's going to be pointing from the positive to the negative charge inside the dielectric. And we will call this one the induced electric field. And you see that the direction of the induced electric field is opposite to the direction of the initial electric field. And what happened to the total electric field? it's gonna be decreasing in magnitude. Let's continue. If the electric field is strong enough, the dielectric breakdown, that means discharge, occurs and the dielectric becomes a conductor. The dielectric strength is the maximum electric field the material can withstand before breakdown. And here we have dielectric constants and dielectric strength of some insulating materials. For polycarbonate, for example, the constant kappa is equal to 2.8 and the electric field strength is equal to 3 times 10 power 7, and so on. Here, for a given separation D between the two parallel plates between the plates, there is a maximum voltage that can be applied to the capacitor without causing the discharge. The maximum voltage depends on the dielectric strength, or we can say the maximum field strength as we show, as we see here. Okay. Then for the air, the dielectric constant is equal 1, and the dielectric strength is equal to 3 times 10 power 6 volt per meter of the electric field. And here we have some properties of the other materials for the dielectric constant and the dielectric strength of various materials at T equal 20. So let me summarize here. When the dielectric is inserted between the two parallel plates of the capacitor, the capacitance increases. The capacitance increases. And there is an increase for the maximum operating voltage of the capacitor, Vmax. And also can provide mechanical support between the conducting plates because there is no vacuum between the plates. So when we add something inside, so when we add the dielectric between the plates, there is a mechanical support to these two plates. Okay, now let's move to the applications of these formulas. A parallel plate capacitor has a plate of dimensions 2 centimeter and 3 centimeters separated by 1 nanometer thickness of paper. Here we have a dielectric with a constant 3.7 and a maximum electric field 16 times 10 power 6 volt per meter. The question, find the capacitance of this capacitor when the dielectric is inserted between the two parallel plates, which is very easy. The question said, what is the capacitance? A. As you know, the capacitance, here we have the dimensions of this capacitor. So it's going to be kappa multiplied by epsilon naught A over D. Okay. So it's going to be kappa, we said it's 3 point, how much? 3.7. 3.7. This is the constant kappa multiplied by epsilon naught 8.85 times 10 power minus 12 multiplied by the surface area of the plate. So it's going to be the length multiplied by the width, 2 centimeter multiplied by 3 centimeter. And don't forget to convert to the meter. So that means we will multiply by 10 power minus 2 from the centimeter to the meter. And and it's going to be divided by the distance between the two parallel plates. I think it's 1 millimeter. So it's going to be 1 times 10 power negative 3 from the millimeter to the meter. And we're going to get the result to be how much? 20 picofarad. So that means 20 times 10 power negative 12 farad, which is equal to 20 picofarad. So this is the capacitance of our capacitor. Question B said, what is the maximum charge that can be placed on the capacitor? What is the maximum charge that can be placed on the capacitor? Question B, as you know the charge, let's say this is Q max, it's going to be C multiplied by B max. However, we don't have this maximum voltage, but we have an information about the maximum electric field. So, as you know, V max equal E max multiplied by the distance. Okay, and we are done. Just we substitute by the numbers. what we call this E multiplied by D, this is V max, the maximum potential difference. So it's going to be, see how much? We said it's 20 times 10 power to the 12 multiplied by E max, how much? We said it's 16 times 10 power 6, 16 times 10 power 6, multiplied by the distance between the two parallel plates, which is 1 nanometer. That means 10 power negative 3. And we are done. So what's going to be the charge, the maximum charge between these two, on these parallel plates? It's going to be 0.32 microcoulomb, 0.32 microcoulomb. Okay, and we are done. Let's move to the third question. In the third question, he said, what is the maximum energy that can be stored in the capacitor? I would like to write the full formula of the energy, the different forms of the energy, the different expressions of the energy. It's going to be half of Q max V max, or it's equal half of C V max squared, or it's equal half 1 over 2C Q Q max squared. Okay, so here you have different expressions and you are free to use whatever you want, but you have to be very careful in the calculation. So it's going to be the half. Let's say, let's use, for example, this C and this Q. So it's going to be half of Q squared. How much? It's going to be 0.32 times 10 power minus 6 squared divided by C, which is equal to 20 picofarad. 20 times 10 power minus 12. We are done. So the result will be 2.6 times 10 power minus 3 joule. 2.6 times 10 power minus 3 joule. And we are done. You see that the questions are not so difficult. Now let's move. Suppose that the capacitance in the absence of a dielectric is 8.5 picofarad. Let me write this and let me take like that. Okay. And I would like to solve step by step. Okay, suppose that the capacitance in the absence of the dielectric is 8.5 picofarad and the capacitance is charged to the potential difference 12 volt. If the battery is disconnected and the slab of polystyrene with a constant, dielectric constant equal 2.56 is inserted between the plates, calculate the energy difference U minus U naught. So from this figure, you see that okay, good. Suppose that the capacitance C 8.5 picofarad and delta V, the potential difference, is 12 volt. If the battery is disconnected and we insert a polystyrene slab between the two parallel plates with a kappa equal 2.56. What happened to the capacitance, as you know, is decreasing. Now, the question is not about the capacitance, it's about the energy difference, U minus U naught. How we can solve this question? As you know, U naught in the absence of the dielectric, let me write. In the absence of the dielectric, what do we have? The energy is equal half of C delta V squared. Okay. However, after, let's write this is not. After, let's write this is C naught, and let's write this is delta V naught. After the dielectric, the energy U will be equal half C naught becomes kappa C naught because after the dielectric, and delta V is going to be divided. So it's going to be delta V naught over kappa because it's decreasing power 2. So what happened to this energy? So we can simplify here by, okay, because we have squared, so we're going to get half of C naught delta V naught squared over kappa. What do we call this? This quantity is U naught. So we can write, so that means U equal U naught over kappa. Now we can determine our energy difference. So we can say that U minus U naught is U how much? So it's going to be U naught over kappa minus U naught. So we can write it's U naught factor of 1 over K, 1 over kappa minus 1. And that's all. Now the question becomes, what is the initial energy from D? We can write like that. Okay. We said that the energy, the potential, the difference in the energy, U minus U naught, is only U naught factor of 1 over kappa minus 1. And U naught, as you know, is half what do we have as given. We have delta V and C. So it's going to be C naught delta V naught squared factor of 1 over kappa minus 1. That's all. Or you can calculate the energy before alone and then the energy after alone, and then you can calculate the difference between them. So I prefer like that. So it's going to be half of C. How much? C 8.5 picofarad. C naught 8.5 picofarad multiplied by delta V naught, which we said is 12 squared factor of 1 over 2 point for the polystyrene 56 minus 1. Okay, so what would be the energy difference according to this results? It's going to be minus 373 picojoule, minus 373 times 10 power 12 joule. And we are done. Okay, so this is the energy difference after and before the dielectric. Now we will move to these questions that I see that they are very good questions. So in this question, you charge a parallel plate capacitor, and then you remove the capacitor from the battery and remove it from the battery and prevent the wire connected to the plates from touching each other. When you pull the plates apart, what happens to the following quantities? If you pull the plates apart, what happened here? What we are changing? You are changing the distance between the two parallel plates. So that means the distance is increasing. Okay, so the distance is increasing. What happened to the capacitance? As you know, C equal for the two parallel plates in the absence of dielectric, so it's going to be epsilon naught A over D. If D is increasing, the capacitance for sure is decreasing. This is the first point. Let's move to the second point, the charge Q. As you know, the capacitor is not connected to anything. So the charge Q on the capacitor will be the same as it's not connected. It's not connected to anything. Okay, what happened to the energy? As you know, the energy as a function of C and Q is equal Q squared over C. This is the same, but this is decreasing, and this is the same. If the capacitance is decreasing, what happened to the energy? The energy will be increasing. Let's move. What happened to the potential difference? As you know, delta V is equal Q over C. Yes or no? Yeah. This is the same as it is not connected to anything. And this is decreasing. So what happened to the potential difference is increasing. Let's continue. What happened to the electric field? As you know, delta V equal E multiplied by the distance. So that means our electric field is equal okay. So as you know, the electric field is going to be delta V over D. So if delta V is increasing, and the electric and the distance between the two parallel plates is increasing also by the same amount, of course. So in this case, what we're going to get, the electric field will stay the same. Okay, let's move now to the second part. You charge a parallel plate capacitor with a battery, and then the battery is still connected, remains connected to the plates. When you pull the parallel plates, the plates apart, that means you increase D. What happens to the following quantities? If the battery is still connected, of course, delta V is the same. Let's start by this because it's very easy. If the battery is still connected, delta V is the same, stay the same. Now what happened to the capacitance? As you know, C equal epsilon naught A over D. And if D is increasing because we are pulling the plates apart, that means the capacitance is also decreasing as before. Now what happened to the charge? As you know, the charge is Q equal C delta V. Delta V is the same because the battery is still connected. And C is decreasing, so that means the charge is decreasing. Now what happened to the energy? The energy, as you know, as a function of delta V, why? Because it stayed the same. So it's going to be half of C delta V squared or Q delta V. So if this is the same, and the capacitance is decreasing, so of course the energy will decrease. Now what happened to the electric field? From the previous equation, we said that the electric field is delta V over D. If this is the same, and D is increasing, so the electric field will decreases as a result. So like that, we are done. As an application of the capacitors, a medical device in which the capacitors have an important role. Up to 360 joule of energy is stored in the electric field of a large capacitor in the defibrillator when it's full of charge. The defibrillator can deliver all of this energy to the patient in about 2 milliseconds, in a short distance. It can be discharged to the body of the patient. The sudden electric shock stops the fibrillation, the random contractions of the heart that often accompany the heart attack. Now, I would like to move to the class activities. You reposition the two plates of the capacitor so that the capacitance doubles. There is a vacuum between the plates, so there is no dielectric between the two parallel plates. If the charge Q plus Q and minus Q on the two plates are kept constant, in this process, the energy stored in the capacitor becomes 4 times greater, twice greater, remains the same, becomes half as great, or becomes 1 over 4 as great. What is the variable here? What we change it? We changed the capacitance of the capacitor. And we are asking about the energy stored. And we keep Q is the same. So here we have to write the energy as a function of Q and C. So it's going to be the half of Q squared over C. If Q is the same, but C is doubled, so we will write half of Q squared over 2C naught. It's going to be U naught over 2. So the answer is 1 over 2 as great, because Q squared, the half of Q squared over C naught is U naught. Okay, and it's going to be divided by 2. So the answer is D. You slide the slab of dielectric between the plates of the parallel plate capacitor. As you do this, the potential difference between the plates remains constant. Delta V is same. Okay. What effect does adding the dielectric have an amount on charge on each of the capacitor plates? What is the effect of the dielectric on the charge? On the charge. As you know, the charge equal C delta V. Let's say this is C naught, Q naught, and let's say this is C naught. This is before. After the dielectric, Q equal kappa multiplied by C naught. And it's going to be multiplied by delta V, because delta V is the same according to this question. So what happened here? And kappa, as you know, the dielectric constant is greater than 1. So what happened to the charge Q? It's going to be greater than Q naught, so it's increasing. So the amount of charge is increasing. Last question. A capacitor with capacitance C is connected to the battery until charged, then disconnected from the battery. The dielectric having constant kappa is inserted in the capacitor. What changes occurs in the charge, the potential, and the energy stored of the capacitor after the dielectric is inserted? The battery is disconnected. Okay, so how to answer this question? Since the battery is disconnected, so the charge will be the same. Q increases? No. Q decreases? No. Q decreases? No. Q stayed the same. Let's check the other properties or the other quantities. As you know, delta V equal C kappa C multiplied by Q. Sorry, delta V is going to be Q over C multiplied by kappa, because C after the dielectric. Q is the same because the battery is connected to anything. However, delta V will be decreasing. Why? Because we will divide by kappa, and kappa is greater than 1. So this is correct. What happened to the energy? U is equal half of C delta V. Let's say, let me write as a function of Q. So it's going to be Q squared over C. Why Q? Because Q is the same. So if C is increasing, because we will add a dielectric, so it's going to be multiplied by kappa. So what happened to the energy? The energy will be decreasing. And the correct answer is D. Thank you so much, and see you in another chapter.